All right, we're going to be moving on from our discussion of vectors onto a new topic, a new unit, a new section of material. And this involves, starts off talking about inverse functions. The goal eventually is to get to exponential functions and logarithmic functions. So the goal is to get to those two topics. Some of you may have had some experience with some of these, and some of your experience might not be particularly pleasant, but we'll see if we can kind of smooth over that. At least get us enough information so that as you go to your, for example, your physics courses or maybe some chemistry courses, and certainly as you go into the calculus sequence, you have enough background, enough basis to be able to work some of this. Now, it turns out that once you get to Calculus 1, you revisit these ideas and you take a little bit different approach to them. And one of the reasons that it's so challenging to discuss exponential and logarithmic functions to students before they've had the calculus is, I think the simplest and best and most straightforward and cleanest way to discuss these things is really with the basis of the calculus. So we're sort of working with one arm tied behind our back, but we can get some of the basic ideas put together here and some of the basic facts that you're going to need, at least for now, and then when you get to the calculus class, you'll expound on them and get them a little bit deeper notions studied. So for now, we're talking about inverse functions, and I think most of us have talked about the notion of functions. Suppose this is a function f that maps this domain to this range. Let's suppose that this is domain, let's call this, suppose the domain is set A, and let's suppose the range is set B. A common way to write this, you may not have seen this before, but a common way to write this, f is a function, A is the domain, B is the range. A common way to write this is f colon A arrow B. This means f is a function that maps domain A to range B. So this collection of symbols represents what we're actually doing here. Now, what this means is we have a value here, A, and it corresponds to the function value, let's say B. We may, if we wish, write B as f of A. So the function value of A, the function rule applied to the value A produces the value B. B is equal to f of A. Now, the notion of an inverse function says this. An inverse function would be a function that takes this as the domain and this as the range, and not just that, it takes this as domain and this as range, and the rule is this: f inverse of any value in this domain is the original value in this original domain, which is the range, the original value in this original setup that caused B to arise in the first place. So if C maps to D, if D is equal to f of C, then what we require is D maps to C using the inverse function rule. So what we have here is we can say, where did B come from? B came from f of A. Where did A come from? A came from f inverse applied to B. D came from f of C. Where did C come from? C came from f inverse applied to D. And so what we see is this. This expression, B is equal to f of A, and f inverse of B is equal to A. Those are equivalent statements. And then D came from f of C. Well, f inverse of D is equal to C. Those are equivalent statements. These two statements and these two statements are equivalent to each other. So that's a key notion in this. Now, when we say A maps to B, then we can express f as a collection of points. We can say A comma B is is a set of coordinates that is generated by this function f. Similarly, C, domain value, maps to D, range value. But for every set of values we have here, f inverse, if it's a function and if it exists, we would say that B is the input, A is the output. So if A comma B is a coordinate generated by function f, B comma A is a coordinate generated by f inverse. Similarly, D comma C. So if f is a function and if f inverse is its inverse function, if this is a function, this is its inverse, then this property holds for all values of A, B, C, and D. In particular, suppose we know for some function f, suppose we know that f of, let's just pick a number out of the blue sky. Let's suppose that f of 3 maps to, let's say, 5. Then what do we know about the inverse function? Then we would know that f inverse of 5, 3 was here, 5 is here. So f inverse takes 5 and puts it back where it started from. And so this corresponds to the point 3 comma 5, input comma output. This corresponds to the point 5 comma 3, input comma output. And so we see this property in behaving here. So that's one of the first key notions of inverse functions. If f is a function and if this is its inverse, we're going to comb through that a little bit yet. But if you have a function and if you have its inverse, then a couple things must be true. We can say that if A comma B is generated by function f, then reverse the coordinates, B comma A is generated by function f inverse. All right? Now, we have one last little piece here. If f is, this is the domain and this is the range, if A is the domain, B is the range, then what do we know about f inverse? F inverse takes this set as the domain and maps it to this set as the range. All right? Roughly speaking, in an offhanded way, we say for a function and its inverse, the domain and range switch places. Now, these are functions, inverse functions of each other. And the last piece we'll leave is this. If this is f, this is f inverse. What is the inverse of f inverse? Suppose we started going from right to left. What is the inverse of this? Well, we could say, what is the inverse of the inverse? Well, the inverse of the, what reverses f inverse? It's the original function itself. All right? And so these are some of the basic ideas about inverse functions. We'll talk about a few more of them in the next video.